Welcome back to Math 111, Elementary Statistics at Georgetown College. This is part 2 of Chapter 4 on 2 numerical variables. Always make sure to load the necessary packages before you begin working. You'll also want to load and view the data sets that will be discussed in this section: M111 survey, UC Davis 1, and Penn State 1. The two topics of discussion in part 2 will be correlation and the regression equation. We'll start with correlation. In the last section of this chapter, we used scatter plots to visually identify the direction of association between two numerical variables. It is also important to consider the strength of association as well. The variables height and fastest from the M111 survey data have a positive association, which we saw last time by looking at the scatter plot. However, the variables height and ideal height have a stronger positive association. This can be seen by comparing the scatter plots. The scatter plot on the left is height and top speed. The scatter plot on the right is height and ideal height. For each pair of variables, we can see that there's a positive association between them. By looking at the cloud of points in both scatter plots, we see that large values on the x-axis tend to go with large values on the y-axis, and small values on the x-axis tend to go with small values on the y-axis. So the cloud of points in both scatter plots appears to be directed upwards to the right. However, notice in the scatter plot on the right that this cloud of points is much more tightly clustered. In other words, there's less scatter in the scatter plot on the right than there is in the scatter plot on the left. This degree of closeness that we're talking about can be measured by the correlation coefficient. The correlation coefficient is the numerical measure of the direction and the strength of the linear association between two numerical variables. The correlation coefficient is denoted by lowercase r, and it's given by the formula you see here. R is in sorts the almost average of the product of the z-scores for all of the points in the scatter plot. First, let's recall what a z-score is. The z-score of a value is the number of standard deviations that value is away from the mean. In other words, the z-score for an x value would be given by this equation: x minus the average of the x's divided by the standard deviation for the x's. So in the equation for the correlation coefficient, each ordered pair in the scatter plot, in other words, each point in the scatter plot, the z-score for the x-coordinate is multiplied by the z-score for the y-coordinate. This gives a sort of measure to how far each point is away from the point of averages. These products are then summed, and the sum is divided by n minus 1. The computation of the correlation coefficient can be rather cumbersome. There's a function in R that computes it for us. So the correlation coefficient for the variables height and fastest from the M111 survey data can be computed using the COR function in R. Notice that the input to this function is the same as the input was for the XY plot function. So we do response variable tilde explanatory data equals M111 survey. The third piece of information that must be supplied to the core function is use equal na.or.complete. This command is necessary to deal with missing values. We can compare this to the correlation coefficient for the variables height and ideal height. For this case, R is 0.832, much higher than the correlation coefficient for height and fastest. For any pair of numerical variables, the correlation coefficient will always fall between -1 and 1. The sign and the magnitude of R indicate different things about the relationship between the variables. Positive values for the correlation coefficient indicate a positive linear association between the two numerical variables. Negative values for R indicate a negative linear association. The magnitude of R tells us something about the strength of the relationship. If the correlation coefficient is identically equal to 1, we have a perfect positive correlation between the two variables. If R is identically equal to -1, we have a perfect negative correlation. If R is equal to 0, we say that we have no correlation between the two variables. The values of R can be investigated further with the Very Correlation app. So let's copy this code and we'll run it in RStudio so that we can see what this app tells us. This app allows you to see what the scatter plot of two variables with a given correlation might look like. When you first open it, the target correlation is set at 0, and you'll see a scatter plot that has a correlation somewhere near 0. You can see that this cloud of points has no real direction and it's very scattered. As we increase our target correlation, you can see that the cluster of points, or the cloud of points, starts to look like it's more directed upwards to the right. The closer to 1 we set the target correlation, the more tightly clustered this cloud of points becomes. If we increase the target correlation all the way to exactly 1, we see that the points in the scatter plot fall on a straight line. We could explore this for negative correlation coefficients as well. As I move further in the negative direction, the cloud of points seems to be directed downwards to the right. The closer to -1 that we get, the more tightly clustered the cloud of points becomes. And if our target correlation is set at exactly -1, we again see that the points fall in a perfect straight line with negative slope. Let's use these ideas to investigate another research question. At UC Davis, how is a student's mother's height related to their father's height? In this case, we'll use dad height as the explanatory variable, and we'll use mom height as the response variable. First, let's plot the scatter plot. When we view the scatter plot, we can see that our cloud of points appears to be directed upwards to the right, which would indicate a positive association. However, the points are rather scattered. They don't form a very tight cluster. So although a positive association is expected, it does not appear to be very strong. When we compute the correlation coefficient, we see that we get 0.2572, so it was positive, but again, not very strong. Now to the regression equation. Any linear relationship can be explained using the equation of a line called the regression equation. The regression equation is used to predict the value of the response variable from a known value of the explanatory variable. The equation is given to be y hat equals a plus bx. Here, y hat is the predicted value of the response variable. X is a known value of the explanatory variable. A is the y-intercept. In other words, this is where the line crosses the y-axis. And b is the slope. In other words, rise over run. Let's see how the regression line is useful in answering the following research question. At Penn State, how is a student's right hand span related to his or her height? We've plotted the scatter plot here along with the regression line. We know that every point in the scatter plot is a known observation. In other words, every point in the scatter plot represents an individual from the data set. Each point on the regression line, however, represents a predicted height for a given value of the explanatory variable. Another thing to notice here is that the regression line is the line that best describes the trend in the scatter plot. For this reason, the regression line is often referred to as the line of best fit. In order to understand what we mean by the line of best fit, we first need to explain what a residual is. A residual is the vertical distance between a point in the scatter plot and the regression line. For example, here we have several residuals plotted in red. So the residual for this point in the scatter plot is just this vertical distance from the point down to the regression line. You could think about calculating this vertical distance by taking the y-coordinate for the point in the scatter plot and subtracting off the y-coordinate for this point on the regression line. Notice that points that lie above the regression line will have positive residuals, and points that lie below the regression line will have negative residuals. The reason that the regression line is often referred to as the line of best fit is because it is the line that minimizes the sum of these squared residuals. So for every point in the scatter plot, the vertical distance between that point and the line is computed, these residuals are squared, and then summed. The regression line is the line that minimizes this sum. We can investigate this further with the Find Regline app. So let's copy and paste into RStudio. This app produces a random scatter plot in the plot window, shown by the blue dots you see here. The X and Y axes are plotted in green. You also see a horizontal black line plotted in with residuals from that line to each of the points in the scatter plot. A couple of other things you'll notice is that the sliders over here allow you to control where the intercept of this black line falls and the slope of the black line. So currently the intercept is set at negative 7.84 and slope is set at 0, so horizontal line. This app operates like a game. It is your job to adjust the intercept and the slope in such a way that you minimize the sum of squared residuals. In other words, you find the regression line. You're told that the minimum sum of squares is 38.3. In other words, the sum of squares for the regression line is 38.3. Currently, where the line is set now, the sum of squares is 125.26. In other words, if you computed all of these vertical distances, squared them, and then added them up, you would get 125.26. The regression line is the line that is the closest to the points in the scatter plot in terms of these vertical measurements. So we want to adjust the intercept and slope to try to minimize the residuals. So it looks like we need to raise our intercept up, let's say to maybe negative 4. Let's try that. Okay, that's close enough. When we did that, notice that these residuals down here got larger. Our sum of squares increased as well to 272. So we need to decrease our slope. So suppose we want our line to go something like this. We can do a fairly good job estimating the slope by thinking about what the rise over run would be. So it looks like our slope needs to go down. So let's go ahead and adjust the slope to what we think might be reasonable. Maybe 0.6. Okay, notice how now the residuals are smaller, and our sum of squares has decreased now to 54.98. Still not the minimal sum of squares, but we're getting closer. So you can toggle back and forth, adjusting intercept and slope. If you want to play this like a game, you can show your score. The way in which your score is calculated, you are penalized for every move that you make. So The goal is to minimize your sum of squares to get as close as you can to the regression line in as few moves as possible. When you decide that you're done and you give up, you can check the checkbox that you quit. It will plot in the regression line. You can see how far off you were. And it will also tell you what the equation of the regression line was. So here our intercept should have been negative 2.19. So we were quite off here with the intercept. The slope should have been negative 1. So you can see how your intercept and slope compare to what the intercept and slope for the actual regression line is. The correlation coefficient, the equation of the regression line, and the graph can all be output in the built-in function LMGC, LM standing for linear model. So if we want to come up with the regression equation to predict height from right handspan in the Penn State 1 data, we can run the LMGC function. The input to this function is identical to the inputs you've been using in this chapter. So response variable, tilde, explanatory variable, and then give the data set. The output will appear in your console as you see here. The correlation coefficient is given for you, 0.63, along with the equation of the regression line. The predicted height is given by 41.96 plus 1.239 times the x value, the right handspan. The residual standard error and the r squared value will be discussed at the end of this part of the slides. If you want to include a graph along with the output of the regression line from the LMGC function, you can add the argument graph equal true, and you will get the scatter plot with the regression line. If you want to see the graph along with the output from this function, you should add in the argument graph equals true to the LMGC function. You will get the output that you saw before in the console along with the scatter plot and the regression line. The regression equation allows us to make predictions. For example, if we knew that a Penn State student had a right handspan of 22 centimeters, we could predict their height by plugging 22 into the regression equation. We could compute this value by hand by calculating this. We get 69.2. So a Penn State student with a right handspan of 22 centimeters is predicted to be 69.2 inches tall by this model. There's a built-in function in R that will also compute this for us. The predict function requires two inputs, a linear model and an x value. So in order to use the predict function, we need to store our linear model in an object. We named the object here hand height mod. And then the predict function requires the model and the value of x. When x is 22, the model predicts y height to be 69.23. The interpretation of the regression line is very important. The intercept for the regression line of the right handspan height model that we've been looking at is 41.9593, and the slope is 1.2394. What exactly do these numbers mean? Recall that the intercept of any line is where that line crosses the y-axis. In other words, it's the y value when x equals 0. So in this case, 41.9593 is the predicted height of a Penn State student with a right handspan equal to 0. Be aware that the interpretation of the intercept in the context of the regression equation does not always make logical sense. The slope of any line tells you how much the y value changes for a 1 unit change in the x value. So for this example, the predicted height of a Penn State student changes by 1.2394 inches as the right handspan increases by 1 centimeter. So for every 1 centimeter increase in right handspan, the predicted height for a Penn State student is increased by 1.2394 inches. Anytime we deal with statistical relationships, there's variation in the data. In other words, a line is not a perfect explanation of the relationship between two numerical variables. We measure this variation in two ways: the residual standard error and the squared correlation. One output of the LMGC function is the residual standard error. We can see that for the Penn State data of right spans and heights, the RSE is 3.149. But what does this tell us? Well, the residual standard error measures the spread, or the standard deviation, of the residuals. Remember, the residuals were the vertical distances between the points in the scatter plot and the points on the regression line. So RSE just measures the variation in these residuals. One problem that is encountered with the residual standard error is that its magnitude is directly affected by the unit of measure of the response variable. Both of these scatter plots were created using the Penn State dataset with right hand span as the explanatory variable and height as the response variable. You can see just by looking at the scatter plot and the regression line that they appear to be identical. The difference between these graphs is the unit of measure used on the response variable. So the scatter plot shown here on the left, height is measured in inches. The scatter plot shown here on the right, height is measured in feet. Regardless of the unit of measure used in the variable height, the regression line in both of these scatter plots does an equally good job of explaining the variations shown in the data. However, the residual standard error for the scatter plot on the left is much higher than the residual standard error for the scatter plot on the right. Being that the scatter plots look identical here, this difference in residual standard error is a direct result of the change in unit on the variable height. In the scatter plot on the left, since height is measured in inches, each of the residuals is going to have a higher magnitude than the corresponding residual will have over here where height is measured in feet. These higher magnitudes are going to cause the residual standard error, the standard deviation of the residuals, to also be higher. For this reason, residual standard error is not the best measure of variation between two numerical variables. The squared correlation is a much better measurement to explain the variation seen in the scatter plot, as it is unaffected by a change in scale. R squared tells us the proportion of variation in the response variable that is explained by the explanatory variable. R squared is the squared value of the correlation coefficient. Since the correlation coefficient is always a value between -1 and 1, its square will always be a value between 0 and 1. R squared values close to 1 indicate that a high proportion of the variation that we see in the y values in the scatter plot is explained by the explanatory variable. R squared values identically equal to 1 imply perfect correlation between the explanatory and response variables. An R squared value equal to 0 implies no correlation between these variables. Part 3 of this chapter will discuss cautions that you should be made aware of when examining relationships between two numerical variables.